Rahim. Dear students, Assalamu alaikum. Welcome to the Electrical Engineering channel. In this lecture, I will discuss the magnetic flux and magnetic flux density. Magnetic flux lines also exist around the magnetic poles, as we discussed for electric flux lines, and electric flux lines exist around the electrical charges. Similarly, magnetic flux lines exist around the magnetic poles, and the total magnetic flux divided by the total area is called magnetic flux density, and magnetic flux density is represented by the symbol of B, and B is equal to mu times H. Here mu is the permeability of the medium and H is the magnetic field intensity. In electrostatics we had D equal to epsilon E. So D was electric flux density, E was electric field intensity, and epsilon was permittivity. Here we had similar relation and B equal to mu H, where B is magnetic flux density, H is magnetic field intensity, and mu is the permeability. Permeability of the medium is defined as the ability of the medium to allow magnetic flux to pass through it is called permeability. And permeability mu is equal to mu naught mu r. Mu naught is the absolute permeability or permeability of free space. Similarly, mu r is the relative permeability. For free space, relative permeability mu r is equal to 1. And for free space, mu will be equal to mu naught. And the value of mu naught is equal to 4 pi into 10 to minus 7 Henry per meter. Total magnetic flux can be found out by the surface integral of magnetic flux density, and phi is equal to mathematically B dot ds surface integral. So this is called magnetic flux. Um, okay, so one important thing is that B is a medium dependent quantity, H is medium independent quantity, because in previous lectures we discussed the expressions for H, and none of those expressions contained the parameter which is specific to the medium, for example, epsilon or mu. So H is medium independent, but magnetic flux density, since it is equal to mu H, so it is medium dependent. In electrostatics, the thing is opposite. The electric flux density is medium independent, but electric field intensity is medium dependent. So in electrodynamics, this thing is opposite. If we evaluate the closed surface integral of magnetic flux density, that will always be equal to 0, and it means that net magnetic flux leaving out the closed path is equal to 0, and the magnetic field lines are circular and closed. So we know that the magnetic flux lines always follow a closed path. So for example, in this figure you can see this is the magnetic flux line, and it is always be a closed line. Similarly, this is one form of magnetic flux, and if we have a magnet, again we will have circular magnetic flux lines. So if we make an arbitrary closed surface around the magnetic flux line, we will see that net magnetic flux leaving out this closed surface is always equal to 0, because within this closed surface magnetic flux lines are originating and terminating, because they constitute a closed path. So no magnetic flux is leaving out this closed surface. So flux leaving out is equal to 0, and flux entering is also equal to 0 in this case. If we constitute such a closed surface in which part of the magnetic flux lines are within this closed surface and part of those magnetic flux lines is outside this closed surface, then we will have such a scenario, and you can see the magnetic flux lines are entering in the closed surface and they are also leaving out this closed surface. So in this case, flux leaving out is equal to flux entering, but the net magnetic flux leaving out or leaving in is again equal to 0. So that's why the closed surface integral of B dot ds is equal to 0, and that can also be stated as no magnetic poles can be isolated from each other. And in electrostatics, the closed surface integral of electric flux density d dot ds was equal to the charge enclosed. So positive and negative charges can be isolated from each other, and electric flux lines always originate from the positive charge and they terminate at the negative charge. And we can make a closed surface which can only contain either a positive charge or a negative charge. So in that case, the closed surface integral won't be equal to 0. But here, if we want to make a closed surface that has to contain both north and south poles, So net flux leaving out will be equal to the net flux entering the closed surface. So no magnetic pole can be isolated in this case. So that is all about our today's lecture, and I hope you have understood the concept of magnetic flux and magnetic flux density. For watching more lectures, please subscribe this channel. Until the next lecture, it's goodbye.